Oh, welcome to Lab 2 on model checking. So in the first lab we covered LTL and all the temporal operators associated with that. And in this lab we'll be moving on to computational tree logic, CTL. So CTL is also a type of temporal logic, however it's concerned with branching time logic. So while LTL operated on linear time transitions, this works on branching time logic. As well as having the logical and temporal operators of LTL, CTL requires the use of additional quantifiers to identify properties that exist across all possible paths that are possible from a given state. So this basically just means that in LTL you remember that every state only had one possible successor because you're always operating on a linear path. As you can see in CTL, like the black node here, we have two possible successors. So we have two possible paths coming off this black state. And this is the quantifiers we need to be able to quantify going down different possible paths. Note that CTL cannot express certain properties that are possible with LTL and vice versa. So we'll go into that in part 2. So again, in CTL we have our logical operators. As we saw, these are the same as what we did in the ADD lib. We have our temporal operators, which we see in the previous lab, in the LTL lab. And now we have path quantifiers, A and E. So this stands for all paths is the A, and exists a path is the E. So this gives us the BNF, the construction of CTL formula, where P ranges over a set of atomic propositions. So phi equals, so we have, again, this is the same as LTL. We can have P true, we can have P proposition, we can have negative phi, we can have our OR. But you'll notice that now we have our A and our E path quantifiers. So for all paths, next phi 1, for all paths until phi 2, exists a path where next is phi 1, exists a path until phi 2. So let's go through the path quantifiers. So A, you can also denote it as this symbol, and an upside down A, or a B with a line going through it, for all paths. So it means for every path. You'll notice that all path quantifiers are immediately followed by a temporal operator. You cannot have a path quantifier that doesn't have a temporal operator afterwards. You also cannot have a path quantifier with two temporal operators immediately following it. So if you have to have two temporal operators, you have to have two path quantifiers. So if you were to say for all paths next and there exists a path always, you have to go AXEG. Can't do AXG. That's just a core thing of CTL. So say here again, must always be followed by a temporal operator. So let's go through A for all paths. A, G, phi. So for all paths, property phi is always satisfied. So this is the same as the LTL formulas. So it's going to be always satisfied. And now we're just checking that this holds across all paths in our tree. So it's going to go this path, and this path. All the paths. That's just what we mean by all paths. LTL actually assumes that it has an A in front of everything. So essentially this is the same as saying G of phi. So LTL, you can always assume that there is an A in front of all the terms. That's for all paths. Except you notice in LTL we can do FG phi. When in CTL we cannot do this. So that's where the difference lies. So for all paths, eventually phi is satisfied. For all paths, property phi is satisfied at the next state. So that would mean if you started at here, phi is satisfied here and here. for all paths until phi. So for all paths, phi strong until psi. So for all paths, property phi is satisfied until it is not, at which point psi is satisfied. Property psi must be satisfied at some point. So again, it's the same strong until as the LTL. Same weak until for all paths, property phi is satisfied until it is not, at which point psi is satisfied. Property psi does not have to be satisfied, but property phi must remain satisfied otherwise. This is across, again, all paths. So exist a path is E, also denoted as the backwards E. Again, must always be followed by a temporal operator. So there exists a path where always phi is satisfied. You notice this is not the same as LTL formula. So there exists a path where phi is always satisfied. So you notice in LTL it was G of phi, so always satisfied. So that must mean phi is satisfied in every single state. Again, for all paths, A, G of phi, same thing. It's going to go check all the paths and make sure phi is satisfied. When we have E, G of phi, there exists a path where always satisfied. Then we only need one path where G, so if it's, let's say if it's red, black, brown, dark green, that could be a path where this is always satisfied. It's not satisfied here, not satisfied over in this path, but it's satisfied in this individual path, and that would be exists a path for G of phi. So it's just one single path. Now there could be two, there could be three, but as long as there is one, then it is satisfied. Exists a path where eventually phi, again, exact same, just a path that satisfies this. Exists a path where next state is phi, so again here, if you're at red, if green satisfies it, or if black satisfies it, then it's true. Or it must be one of them. Or for here, it has to be brown or yellow. Or both. Exists a path until phi, so again, exists a path phi, strong until psi, exists a path. So this is exactly the same again. And weak until is the same as well. So you just gotta know that for all paths, and there's three things you must know. So for all paths, it's every single path. For exists a path, it's just one single path will suffice. You can't have more than one, but one is all you need. And a path quantifier must always be followed by temporal operators. And you can only have one temporal operator per path quantifier. So they're the three main things to know about CTL.